So, hello everyone, welcome to lecture 24. So, in the previous lecture we have constructed our first composition versus temperature phase diagram, and that was called the isomorphous phase diagram. And the way we constructed it is, we said, alright, there are two phases that we need to consider, the alpha phase and beta phase, or the liquid phase and solid phase. In both phases, so both components A and B, and A can be platinum, palladium, hafnium oxide, zirconium oxide, whatever it is, right. So these components can they like each other, so they will form ideal solutions. It does not matter whether I am in a liquid phase or a solid phase, in both phases the solutions are ideal. And if solutions are ideal, then we did this analysis, right, so of tracking the free energy as a function of temperature of both the phases, the red and the green, right. So at some point, so first the green, which is the solid phase, is up, right, and the red, which is the liquid phase, is down, right. So at very high temperatures, but at some point the red starts crossing the green, right. So that starts at the melting point of 2, and so then there is a phase coexistence if we do this tangent rule, right, or common tangent rule, right. So there is a part of the composition where only liquid is stable, there is a part of the composition where only solid is stable, but there is a part of the composition where the phases want to segregate out. So right, so there should be a liquid phase with a different composition, a solid phase with a different composition, and so that's the equilibrium state, right. So the mixture or the heterogeneous mixture becomes the equilibrium state there, right. And we can combine everything and then say, all right, so I can make a phase diagram which is like this, where this line is called the liquidus line and this line is called the solidus line, right. And in between the liquidus and solidus I have a coexistence of liquid and solid phases, right. And above the liquidus line it is the liquid phase that is stable, below the liquidus line it is a solid state that is stable. So as a function of temperature versus composition of x2, so I have so I have the phase stability, right. So this is my first phase diagram, or this we said is called the isomorphous phase diagram. Okay, so now using this simple isomorphous phase diagram, we have studied the idea of what is called zone refinement. And zone refinement, so I gave you the example of silicon plus some impurities, right. So although I mean the phase diagram of silicon plus impurities can be more complex, right. So in a part of it, let's say only in this part I can look at it to have this sort of a shape, or the isomorphous like shape. And so how can I make 90% pure silicon to be more pure, right. So I heat it, I cool it down, right. So we looked at this, I heat it, I cool it down, and once I cool it down I already precipitate out a solid with larger percentage of silicon, larger purity, and so I have to separate it out from the liquid, right. So and this happens through the so called zone refinement technique, where so this melt phase is taken away by taking away the heater, or by physically moving the sample, moving the ingot, right. So this melt phase is taken away, so the solid liquid equilibrium goes away and the solid that is formed has a higher purity, right. So it's as if I am sweeping away all the impurities to one side of my ingot, right. So if this is my ingot, by melting and so taking away this melt phase away from this region, I make this solid, right. So this solid more pure, and so on. So as a result the impurities are being swept away, sweeping in the impurities. Right, into the liquid phase. They are in the liquid phase, but the liquid phase it's just being swept away. Okay, so as a result I end up with solid that is more pure. I can run this several times, right. So I can run this the same same zone refinement several times to get from 90% pure to 99.999% pure silicon, right. So this is the idea of what is called zone refinement. Okay, now you can check out YouTube videos on how zone refinement is really done I cannot show you, but so you can see even right now in standard labs you have single crystals that are zone refined, so to much more purity, and you can actually see that, right. So even in academic labs this zone refinement setups do exist. Okay. Now that is the first phase diagram, right. So now let us increase the complexity of the phase diagram a bit, right. So so we started by saying that both alpha and beta phases form ideal solutions. Now beta is typically a high temperature phase and alpha is a low temperature phase. Let us do the definition right away so that we don't get confused later on. So for beta I can use a liquid, for alpha I can use a solid. Okay. Now I'm going to add in the caveat that alright, so in a liquid phase, right, so things want to mix more easily in liquid phases rather than in solid phases, right. So in solid phase I have this interaction between the atoms that is much more pronounced because the atoms are much more closer in some sense than in a liquid phase. Let us assume that is the case, right. So an alpha phase I am going to represent by a regular solution model, whereas and with omega positive, right. So left to itself the alpha phase, so as you keep reducing the temperature, the alpha phase will start segregating out. This is what we have seen, enthalpically segregating out, and beta phase is described by ideal solution model. Okay. Now if you remember the delta G mix of alpha phase, right. So at high temperatures it looked something like this, as I so this is enthalpic term plus entropic, right. If you remember, enthalpic term was this way. Okay, so let me draw it in a different color. This is the enthalpic term, this is delta H mix, and the entropic term has a larger slope and goes like this, right. So but this is dependent on temperature. Okay, so this is delta S mix or T delta S mix. Okay, so both of them add up, and at high temperatures the entropic term wins. Okay, and as you keep reducing the temperature, there comes a temperature, this is T high, there comes a temperature where this is very flat, right, and this is the total delta G. Okay, so which is equal to delta H mix plus T delta S max. Okay, and at some point this starts to split up, right, and it is at this point we said that look, if I start with a composition which is here, this composition will split up into alpha 1 and alpha 2, right. So I have a spinodal decomposition. It is an instantaneous reaction that just decomposes into alpha 1 and alpha 2. Okay, so so that's the sort of that is just to remind you of what happens in alpha phase, right. So as you keep reducing the temperature, so this is what should happen in alpha phase, right. So this is the trajectory of alpha phase with temperature. It prefers segregation, right. So here it prefers segregation. Now instead of drawing everything, I am going to show you on a PowerPoint as to what exactly happens, right. So when I have, again it is the same thing. So I have a liquid phase, I have an alpha phase, liquid phase is like my beta phase, alpha phase is my low temperature phase, right. Now the only difference between an ideal solution and a regular solution is, in ideal solution both the curvatures of liquid in ideal solution of alpha and liquid, the curvatures of delta or G are the same. They may be tilted a bit, right. So one is tilted this way, the other one is tilted this way, but the curvatures are the same. This is alpha, this is liquid, but curvatures are the same. At any temperature the curvatures are the same, right. Whereas here, so if I look at the expression, so I'm just going to add an omega 1 x1 x2, right. So to the total entropy term, to the total free energy, and this omega x1 x2 is, for example, I have an ideal solution where delta G mix versus composition looks like this. It's just entropic. To that I add omega x1 x2. Again, it's the same exercise that we have done earlier. So omega x1 x2 is going to be like this, right? And so what results is so this is delta G mix ideal. The blue one is delta G mix ideal. This is omega x1 x2. So what results then is another curve where so that is the shape of it, right? So let's not worry about where exactly the delta G is, but this is the delta G mix of the regular solution, right? So the shape of it has a larger curvature, or it is larger. This is larger curvature, right, than ideal solution, or larger radius of curvature. Curvature is defined as, right, so this is a larger radius, this is a smaller radius, right? So larger radius of curvature than ideal solution, or smaller curvature, right? So just to confuse you even more, curvature is the inverse of radius of curvature, right? So smaller curvature than ideal solution. Okay. So very physically you can just imagine that this is more flattened out than the ideal solution delta G. Okay. Now if that's the case, let's go back here, right. So you can clearly see that alpha is more flattened out than liquid, and that and when temperature equal to Tm2, of course there is one point where both of them combine. So this is the only point where alpha and liquid can coexist, and so that's a pure compound. This is pure x2 pure, this is x1 pure, okay, or x2 equal to 0. So since this is the 2 has a higher melting point than 1, this is the only point where they both can exist together, right. And then so alpha then starts to cross liquid, just like so here if I look at it, alpha starts to cross liquid, and so here I can say that until this point, so I can draw a common tangent and say that until this point I have liquid, from here I have alpha plus liquid, and above, let's say here I have alpha, right, which is stable. Okay, so I have a mixed phase that is forming just like earlier, and at some point I will have two intersections, not just one intersection, and that point happens to be T equal to Tm1, right. So I am pulling the L downward, I am pushing the alpha upward, and I will have two intersection points, and there is a region where I have two intersection points, and so I have two what are called miscibility gaps, right. So here I have a liquid, let me draw it properly. At some point I'll have alpha goes like this, the liquid goes like this, and this is liquid, this is alpha. So I will have two what are called, so I can draw a common tangent here, I can draw a common tangent here. So I have so before this common tangent, this is the alpha phase, that is the liquid phase. I have alpha that is stable, right. So in this composition range it is alpha plus liquid that is stable. Again here I have alpha that is stable, here again liquid that is stable. In this region again it is alpha plus liquid that is stable, and beyond that region, right. So this is x2 equal to 1, this is x2 equal to 0, I have alpha which is again stable, right. So I have two regions in composition which have alpha plus liquid, right. So alpha plus beta exists in two different composition ranges. One has so one at larger x2, that is this, and one at smaller x2. That is this range. Okay. So this is called two miscibility gaps. Okay. So, it is not one miscibility gap, I have two miscibility gaps, right. So, this is one, this is the second one. Okay. So, I have two miscibility gaps here coming up. Okay. Now, I further cool it down, then there comes a point T equal to T star where alpha hits the liquid only at one spot, right. It is as if I can so if I am at this composition X star, I have a liquid, I have an alpha phase, and liquid to alpha melting liquid to alpha solidification happens at one X star, right. So, it is as if I am melting a pure compound, right. So, this is called congruent phase transformation. If I take a pure material, so I will have just one melting point, right. So, melting point is uniquely defined, right. If I have an impure material, let us say an isomorphous material, right, and I ask you, this is liquid, this is solid, I ask you where is it melting, I am saying that okay, it starts melting here, it ends melting here, right. So, I have a range of temperatures for this is temperature, range of temperatures or melting temperatures typically exist for solution, right. But at the T star X star point, right, where alpha phase is this way and liquid phase is this way, right. This is liquid, this is alpha, right. So, this is again G versus X, right. So, at that temperature T star, I have a unique composition, right. So, I think so at a given temperature, what is the composition of the liquid phase, what is the composition of the solid phase, I will have a range of compositions, right. So, in case of in a general solution at a given temperature, if phase transition or solidification were to happen, okay. So, generally there is a range of compositions across which solidification occurs. Only in a pure material, does solidification occur at a unique composition, right, unique temperature and composition, and composition is 1, typically X2 equal to 1, that is your pure material. Okay. Now, here what I am saying is I have an impure material. In the case of congruent melting, means I have an impure or a solution right, but that solution melts at one temperature and one composition, okay, as if a pure material or pure element, pure component melts, right. So, it is as if I have it is a pure material that is melting, there is no change in composition, right. Here for example, there is absolutely no change in composition, whatever is the liquid composition is the same as the solid composition, right. So, whatever is the liquid composition which is X star is the same as solid composition, there is absolutely no solute segregation or no change in composition. Okay. So, liquid just directly goes to alpha, and this is called congruent phase transition or congruent melting. Okay. Now, below that alpha, you can see alpha is getting flattened out, alpha is still stable as one phase, but it is getting flattened out. Okay. And so at a temperature less than the critical temperature, and the critical temperature defines for me where alpha starts to split up. Okay. So, alpha starts to split up, and when alpha splits up, so I do not have any stability of alpha, at least in this range where d2g by dx square is less than 0, that is the curvature is negative, I do not have any stability of alpha, alpha comes down to alpha 1 plus alpha 2. Okay. So, so this is the so called spinodal decomposition. And we have seen this before, right. So, alpha phase just spinodally decomposes into alpha 1 and alpha 2 below a certain temperature. Okay. Now, let us go back to this idea of spinodal decomposition. There is no liquid anymore, it is just spinodal decomposition of alpha phase, right. So, so I have this is splitting up, right. So, this is my delta G mix, but okay. So, G mix in general versus x2. Okay. Now, if I start with this composition, this composition will spontaneously split into this composition and this composition, right. So, this is I start with an alpha phase of this composition, it spontaneously splits into alpha 1 plus alpha 2. Okay. Now, how does this spontaneous splitting happen, right. So, here we define the idea of instability and metastability. Okay. Now, here let us say so the alpha phase has a profile like this in this region, right. So, in this region where d square g by dx square is less than 0, alpha is unstable, right. So, the free energy curve curves upward, right. So, the curvature is negative. Okay. So, it spontaneously decomposes as we have studied earlier, right. Now, alpha is 50-50 to start with. So, how does it spontaneously decompose? If I draw just the composition as a function of space. Okay. So, initially alpha is 50-50, I reduce the temperature, right. So, then okay, so then there is going to be a fluctuation that begins, right. So, this is at a temperature, so I reduce T less than Tc. Okay. So, and this fluctuation starts to grow. Okay. This is fluctuation in composition, right. So, this fluctuation starts to grow until so I get this phase which is all alpha 1 and this phase which is all alpha 2, or this phase has the composition of alpha 1 and this phase has the composition of alpha 2, or the other way around, right. So, here alpha 2 has a higher composition and alpha 1 has a lower composition, right. So, first there is a fluctuation that develops and this fluctuation just amplifies, fluctuations or compositional fluctuations amplify, right. So, this is the nature of what is called spinodal decomposition, right. And if I look at the microstructure of something that has spinodally decomposed, right, the microstructure of spinodally decomposed phase, you will see some kind of periodicity, right. So, it just periodically breaks up into phase 1 and phase 2, phase 1 and phase 2, right. So, I mean there is very nice reasons why periodicity comes up, so for now you can just think of the nature of periodicity as thermodynamics is driving the splitting into P1 and P2, but if I make it into P1 and P2, thermodynamics prefers segregation, right. But if I make P1 and P2 phases, what I am also creating is these boundaries, phase boundaries, right, surfaces which are surfaces, right. So, surface energy is the cost that you should pay, is the cost that one should pay for segregation, right. So, as a result, so one force prefers segregation, another force coming from surface energy wants to minimize the number of surfaces. Okay. The only way this can happen is to create some kind of a, so the not the only way, but so there will be, these two are fighting with each other, these two factors fight with each other, right. And typically when there is a some kind of a long range force fighting, or long range repulsive force fighting with short range attractive forces. Okay. So, then what we get is some kind of a periodicity, right. So, here for example, what is the long range force? Long range force is the force of the phase boundary, right. So, phase boundaries energy, right. So, that is some kind of a surface energy that results in so some kind of a long range force, right. Now, what is a short range force? Short range force is the force between AA, or the attraction between AABB, right. So, this is generally preferred, right. AABB configuration is preferred, but for me to segregate like that I have to create these phase boundaries, right. So, there is a driving force for this to form, right. So, A phase to form, but surrounding it should be the BBBB phase, and A phase is separated out from BBBB phase with a phase boundary. Phase boundary has some extra surface energy. So, I have to put in some extra energy, right, and this extra energy does not want BBBB, it ideally wants AB to be combined, so that it does not have to form this surface boundary, right. So, it is a repulsive, or in some sense it is not letting this segregation happen. So, it is like a repulsive force, right. So, in the long range. Okay. So, when those two interact, I get what are called periodic patterns, right. So, and if you are studying patterns, so there is nothing like spinodal decomposition, right. So, I get beautiful patterns that come out of, that emerge out of various systems. Okay. So, classic example is your sand dunes in desert, right. So, there is a wind force which is a long range force that is trying to move away all my sand particles, okay, and there is this attraction between sand particles. Sand particles want to stay close enough to each other, right. So, that is the short range attraction. Wind is trying to throw away the sand particles, whereas the attractive forces between sand particles wants to keep them together. As a result, I get these sand dunes, or some kind of patterns that emerge. Okay. So, this pattern formation is a very beautiful area of physics where I have two competitive forces, right. So, and two competitive forces, one sort of longer range, one sort of shorter range, then both of them combine together to form to give rise to patterns, right. Yeah. So, pattern formation is quite important in material science, right. So, there are lots of cases where you see these patterns that are forming, and so you want to be able to use it to your advantage. Okay. And spinodal decomposition is one such case where I have nice patterns that are forming, right. So, there is phase segregation, but this phase segregation happens as patterns. Okay. Now, spinodal decomposition occurs in this unstable region, right. So, in the unstable region where d2g by dx square is less than 0, that is where I have a spinodal decomposition. Or pattern formation. Okay. But there is another region here, right. So, if I draw a common tangent, the common tangent is not just from here to here, right. It is saying that there is no phase segregation not just from here to here, but there is also phase segregation in this composition range, right. So, x1 dash to x1 double dash, and x2 double dash to x2 dash, right. So, there is, according to common tangent construction, there is phase segregation even from x1 dash to x1 double dash and x2 dash to x2 double dash, right. However, here the phase segregation comes from alpha, which is a stable phase, Stable meaning dou 2 g by dou x square is actually greater than 0. So, here alpha has some stability, but it is just that it is not globally stable, right. So, alpha 1 plus alpha 2 is globally stable. Okay, if it splits up into alpha 1 and alpha 2, the g of alpha 1 plus alpha 2, right, as we have shown earlier, is less than g of alpha, right. So, this gives alpha 1 plus alpha 2 mixture a global stability, but by itself alpha is a metastable state, right. It is not an unstable state. Okay. Now, in that region x1 dash to x1 double dash and x2 dash to x2 double dash, what I have then is what is called a miscibility gap. Okay. And in the region x1 double dash to x2 double dash, I have alpha is unstable, alpha will spontaneously decompose into alpha 1 and alpha 2, right. So, this is spinodal decomposition. Typically, if you see patterns, patterns indicate that I have a spinodal decomposition. If I do not see patterns, if I see some, so alpha 1 is here, alpha 2 is here, right. So, there is some phase segregation, but it is very inhomogeneous, there is no pattern, no pattern formation. I mean, patterns can also form if there is stress, but let us come back to that later. But if I find that there is no pattern formation, then I am quite sure that the parent phase is metastable, right. But if I find that alpha 1, alpha 2, alpha 1, alpha 2, there is some nice patterns that are formed, or patterns meaning periodic patterns, then I can conclude that okay, so this comes from a spinodally decomposed parent phase. Okay, and that is exactly what happens in this phase diagram. If you look here, right. So, in this region I have spinodal decomposition, and in this region, right. So, I have a miscibility gap, and I am going to, in the phase diagram, once I combine all these aspects that are happening, then you can see that look, this is where my liquid phase is stable. This is so liquid plus alpha, this is also liquid plus alpha, right. And then there is one point which is point of congruent melting. I put all these g versus x as 1 t versus x diagram, right. So, this is the phase diagram, second phase diagram, t versus x, right. So, this is one miscibility gap, this is 2 miscibility gap, and here I have a melting point, a congruent melting, just like a pure compound is melting, or pure element or pure component is melting, right. And here I have just an alpha phase, but this alpha phase itself is going to split into alpha 1 and alpha 2, but if I follow this trajectory of temperature and composition, this is where, right. So, it has spinodally decomposed into alpha 1 and alpha 2, but if I follow this trajectory, this is where it has miscibility, it just split up as a metastable phase splits up into alpha 1 and alpha 2, right. So, so this tells me that the alpha phase itself is unstable, but this tells me so between this parabola or this line and this line, or this trajectory, or whatever, this inverted u and this inverted u, right. So, the alpha phase is stable, but is metastable, right. So, it is still splitting up into alpha 1 and alpha 2, but it is a metastable state, right. So, this defines the miscibility gap, but this defines the spinodal decomposition. Okay. Now, very quickly, right. So, before I end this course, end this class, let us see, I told you that okay. So, if that is the case, then you should be okay. So, this is the example of a gold nickel alloy, so the exact same thing that I have been showing you, right. So, gold nickel alloy, you have, this is your x star t star, where you have the spin congruent melting, right. And so in the liquid phase, this is like a an ideal solution. In the solid phase, this is a regular solution, right. So, here I have the alpha solid phase, but then the solid phase itself starts splitting up into alpha 1 and alpha 2, right. So, somewhere here is the pure alpha 1 and somewhere here is the pure alpha 2. Okay. Right. So, this splits up into alpha 1 and alpha 2. Alpha 1 is almost pure gold, alpha 2 is almost pure nickel, right. So, they have absolutely zero miscibility, okay, or they have almost close to zero miscibility as much as possible, okay. But there will be a spinodal decomposition also here, which is not plotted here, right. So, this is the miscibility gap and there will be a spinodal decomposition happening in this phase diagram, okay. So, this is how you read out these phase diagrams, and here I have alpha plus liquid, here also I have alpha plus liquid. I have two miscibility gaps in the high temperature region, okay. How do I use this idea of spinodal decomposition, and let us end here, right. So, for example, this is these are set of works, so from various papers where people have used spinodal decomposition to actually create patterns, right, or engineer patterns in a way that they want, right. So, for example, I want a heterostructure. So, for so this is titanium oxide and vanadium oxide, right. So, what I do is thin films. Okay. So, on a substrate, this is a substrate, this is something like silicon or whatever substrate it is, I do not remember what substrate this is, right. On this substrate, I am going to deposit a solution of titanium oxide plus vanadium oxide at high temperature, right. At high temperature the alpha phase is stable, right. So, titanium oxide, vanadium oxide high temperature phase or beta phase, right, alpha phase. Okay. So, at high temperature alpha phase exists as a one solution, right. Now, as I keep cooling the temperature down, alpha phase will then spontaneously split into titanium oxide rich and vanadium oxide rich regions, like you can see here, right. So, I have to cool down, right. So, once I grow at high temperatures inside a chamber, inside a vacuum chamber, I deposit this film, right. I am not showing you what happens at high temperatures. At high temperature, I have a nice alpha phase, which is a mixture of, which is a nice solution of titanium oxide and vanadium oxide. But as I cool it down, right, so at room temperature, it spontaneously segregates into a vanadium oxide rich region, titanium oxide rich region, vanadium oxide rich region, titanium oxide rich region, and as a result, what I am getting is a heterostructure, right, and this is a lateral heterostructure. So, I am getting films in this direction, okay. Now, I can change the conditions a bit, right. So, this is a problem of pattern formation. How exactly do you form patterns? You can influence the pattern formation to strain and other things, right. So, I can change the conditions a bit and I can make these parallel heterostructures into vertical heterostructures, right. So, lateral heterostructures into vertical heterostructures, right. So, this is again vanadium oxide, this is titanium oxide, the white one is titanium oxide or the other way around. So, here I think you can see it here, right. So, this is what is called the EDS curve. The blue one is vanadium oxide, the green one is titanium oxide, blue one is vanadium oxide, green one is titanium oxide, right. So, as a result, I am actually creating these heterostructure junctions, right. So, like PN junctions or something like that, right. So, I am creating two different types of heterostructures. Okay. So, in one case there is titanium oxide plus vanadium oxide solution, which I am going to call the alpha phase on a substrate or substrate 1 at high temperature. Okay. So, I have flux of titanium oxide, flux of vanadium oxide that came and made this film. Let us look at this example more detail, more carefully in the next class. But this is at high temperature. Once I cool it down, right, the substrate strain etc. are such that I have heterostructure of titanium oxide, vanadium oxide, titanium oxide, vanadium oxide, right, and so on. So, these interfaces are so nice and they are in this direction, right. And these interfaces are important because titanium oxide, vanadium oxide have different properties, interface has interfacial fields and things like that. So, the interfaces are important for electronics, right. So, I created what are called lateral interfaces. Okay. In another case, I tweak how this pattern is formed from spinodal decomposition. I again cool this, but with a different set of substrate strain conditions, right. So, we will look at strain conditions later, but with slightly different set of strain conditions, and now I get what are called vertical heterostructures. This is vanadium, this is titanium, this is vanadium, this is titanium, everything on a substrate. Okay. Now, typically getting these vertically aligned nanostructures, these are called, right. So, vertically right. So, getting these horizontally aligned nanostructures are fine. We can just first give titanium oxide, then give vanadium oxide. I can grow it like this, right. So, layer by layer, right. So, first layer of another layer of titanium oxide, titanium oxide, titanium oxide, another layer of vanadium oxide, vanadium oxide, vanadium oxide, right. So, I can create a heterostructure just by growth. I do not need to use spinodal decomposition, right. But to create these vertically aligned nanostructures, there is no other way except to use spinodal decomposition. There is no other way. Okay. All right. So, let us actually stop here because we are running out of time in this class, and again start this discussion at this point in the next class, right. So, I'll try to give you a more detailed view of what these vertically aligned nanostructures are, so for what purpose do we need vertically aligned nanostructures, for example, right. So, we are going into 3D integration and things like that in transistors, right. So, it will be nice to grow things vertically, p-n junctions vertically up, not just these flat junctions, right. So, if that comes directly out of my growth chamber, that is ideal for me, and so something like a spinodal decomposition can be used in your favor to create these vertically aligned nanostructures, right. So you should do some engineering, but so the basic idea is to use spinodal decomposition. Okay. All right. So, we have seen the second phase diagram, we have seen the examples of spinodal decomposition in this class, and in the next class we will continue on this aspect and then try to see how to form various nanostructures just by looking at phase diagrams. Okay. So, and then we will go to eutectics. All right. Thank you very much. I will see you again in the next class. Bye bye.